Here's a question from complex numbers. Let alpha, beta, and gamma be the distinct roots of the cubic equation, and then they provide you this equation. So let's start by writing that cubic down. X cubed plus ax squared plus bx minus 54 equals 0. They tell us they've got alpha, beta, and gamma, the distinct roots. Alpha, beta, gamma are the distinct roots. That means they're just not equal to each other. They're separate or distinct. A and B, these two coefficients here, are real numbers, so I'll write that down. A and B are real. And then you get these two equations which relate all of the roots to each other, alpha, beta, and gamma. So I've got alpha squared plus beta squared equals 0, and alpha squared plus beta, sorry, that's a gamma, squared is equal to 0. Alright, so now I have to start thinking about all these different relationships here. Part 1, explain why beta plus gamma equals 0. So required to prove that beta plus gamma equals 0. Now the first place I go to think about this is these two equations in here. Alpha squared plus beta squared equals 0, and alpha squared plus gamma squared equals 0. I can see there's a clear relationship between them. There's so much in common. So I'll call one equation 1, call the other equation 2. So how should I put these together to get a relationship between just beta and gamma without the alpha squared in the way? And the answer is, well, if I subtract these two equations from each other, that'll eliminate the alpha squared. All that'll leave me with is beta squared minus gamma squared. And because this is difference of squares, I can factorize that like so. Okay, so now if I solve for beta, I've got two solutions. From this factor, I've got beta equals gamma, and from this solution, I've got beta equals negative gamma. But immediately you can see an issue, namely that because we said right at the outset that alpha, beta, and gamma are distinct, they're not equal, therefore I can say beta can't equal gamma. They can't be the same root, so I can reject this solution. So beta equals negative gamma only, and if I move that gamma over to the other side, then I've got beta plus gamma equals 0 as required. Okay, so far so good. Now let's have a look at part 2. Part 2 says, explain why alpha, the other root that we haven't talked about yet, explain why alpha is real. So, part 2, I am required to prove that alpha is real. So how do I go about this? Well, I now can think about using this what I've just used, what I've just proven here, this result. I'm going to use that because the question has this important word, hence. It says, hence explain why alpha is real. So I'm going to use part 1. So when I look at what I've just proven, beta plus gamma equals 0, this clearly has to do with sum of roots. When you've got a polynomial here in terms of all of its coefficients, you can get the relationships between the roots using Vieta's results. So if you can't remember what those look like, for instance, the one that relates to this one, the sum of the roots one at a time, alpha plus beta plus gamma, would be equal to minus a, that's this coefficient here, on 1. Well, that's just negative a. Okay, but beta plus gamma, that's equal to 0, right? So alpha plus 0 equals negative a, so therefore alpha on its own, that's negative a. And since a, we said at the beginning, that coefficient there is real, since a is real, then negative a will also be real. So there we go, alpha must be real. Okay, so then, let's move on. Part 3 says, hence or otherwise, explain why beta and gamma, these two roots up here, are complex and purely imaginary. Okay, so where are we going to go to look at this? I know that alpha is real, and beta and gamma are related in this way. Beta plus gamma equals 0. So I'm going to use the fact, I'm going to go back to this first equation here. I'm going to say, look, I've got this relationship, and I also know some things about alpha now. It's equal to negative a. So let's put those two together. I'm going to substitute one into the other. So I'll say, since, this is part 3, since alpha equals negative a, I'll substitute into that first equation, which I called 1. Okay, so that means that, alpha squared plus beta squared equals 0 is what was given to us, but I know that alpha is negative a, so I've got this. Okay, the double negative here will cancel, so I've got a squared plus beta squared equals 0. Don't confuse your a with an alpha. Okay, so if I try and solve for beta right now, I've got negative a squared on this side, right? Which means that beta must be, now because this is a negative number, that's where you're going to get the imaginary stuff from, right? So I'm going to get plus or minus a I, right? Which means that whichever of these values it takes, that means that beta is purely imaginary. There's no real part to this. There's no, a plus bi sort of thing. This is just imaginary. So there you go. Beta is purely imaginary. Now, because I know that beta is equal to negative gamma, right? That means that gamma will be, rather than plus or minus AI, it'll be minus plus AI, because if beta's positive AI, then gamma will be negative, and vice versa. Okay, so therefore, and this is from part 1. Therefore, because again gamma has no real part to it, gamma is also purely imaginary. Okay, so that's really good. I've got knocked down 3 parts out of 4. Let's have a look at this last part. Part 4, find a and b. Find out what these coefficients of the original equation are. Okay, so where are we going to go for this? I've already used the sum of the roots here. Is alpha plus beta plus gamma. But because I know all these things about how alpha, beta, and gamma relate, I'm going to now use my product of roots 3 at a time. That's alpha, beta, gamma. And that's going to be, if this is the sum of roots 1 at a time is negative a on 1, and then 2 at a time would be b on 1, and so 3 at a time, that's the product of the roots, would be negative 54. So that's just going to be 54. So I've got this. Okay, that's the product of roots. So how am I going to use this? Well, I know tons of stuff about alpha, beta, and gamma and how they relate. For instance, I know that alpha is negative a. I've got beta in there, and I also know that gamma is negative beta. Right, so that's 54. Okay, well, hold on a second. I also know that what I've got here is these negatives are going to cancel. So I've got an a out the front and a beta squared here, which is also equal to 54. But hold on a second. I had a beta squared up here. I'll just call this, because I got this from equation 1, I'll call this point in the working 1a. So I can say, since beta squared equals negative a squared from equation 1a, I can say that this is going to be a times negative a squared. That's 54. Okay. So wait, hold on a second. I've got negative a cubed equals 54. So a cubed equals negative 54, like so. So a is equal to negative 54 to the power of a third, or the cube root of 54 if you like it that way. So that's really good. I've got the value of a. So now how do I work out the value of b? How do I use this? Well, I use the sum of roots 1 at a time here. I've used the product of roots, or the sum of roots 3 at a time. The last sum and product of roots, or last of Vieta's results that I haven't used, is the sum of the roots 2 at a time. So that is alpha beta plus beta gamma plus alpha gamma. That's all of the pairs that you can make. And if I go back to my original, it's going to be b on 1. That's just equal to b. Okay, but in here, I can substitute a whole bunch of things. I mean, I know alpha. I already know that's minus a. You got a beta there. And I've got beta times negative beta, because that's just gamma there. And then I've got a negative a again and a negative beta again. That's all equal to b. Okay, and this is really good because I can see that these terms and these terms are exactly going to cancel. That's a plus a beta, and that's a minus a beta. So all I'm going to be left with is a beta squared, or a negative beta squared on this side, and a b on this side. So what I've got is this negative beta squared. I can take that negative over there, and I already know from equation 1a, which I noted here, that beta squared equals negative a squared. So that's negative a squared in there. Okay, cool. So rearranging, because I know what a is, I want to solve for b. I've got b equals a squared, and that means it's 54 to the power of a third, or I should say negative 54 to the power of a third squared. So that's 54 to the power of 2/3 when you use your index laws. Now, I'll admit that looks a bit awkward. Negative 54 to the power of a third. That's my a value. Negative 54 to the power of a third, and 54 to the power of 2/3, that's my b value. But if you slip them back into the original equation, just to confirm things, you don't have to do this, but just to settle it for yourself, you can see that back in the original equation, it'll look like this. X cubed minus 54 to the third x squared plus 54 to the power of 2/3 x minus that 54 which we had in the original. Now, this is really easy to factorize because of the numbers that we've chosen, right? For instance, here I take out a factor of x squared, and that gives you x minus 54 to a third, okay? Over here, I'll take out a factor of 54 to the power of 2/3. Now, here, that's obviously just going to give you x. When you divide 54 by 54 to the power of 2/3, your index laws tell you that'll be 54 to the power of 1/3. Okay, so now I've got this common factor, x minus the cube root of 54, and then the other guys, you've got an x squared plus 54 to the power of 2/3. Okay, now, because this is complex numbers, we can actually factorize further, because here, this is difference of squares if you include an I squared in there, right? So you got x minus 54 third, x squared minus 54 to the power of 2/3 I squared. That I squared will be a -1, and it'll cancel with that, which gives you back the original. So now that it looks like difference of squares properly, I can factorize it, which gives me this, 54 to the power of a third, x minus 54 to the power of a third I, that's the square root of this, and x plus 54 to a third I. So these numbers here, they're all the cube root of 54, in case you don't like that index notation, okay? Which means that x is equal to, here are my solutions, 54 to the power of a third is what I get from this factor, or what I get from these two factors is, it's plus or minus 54 to the power of a third I. And this satisfies all our original things. This thing here, right, is alpha. These two solutions here are beta and gamma. They're purely imaginary. All three roots are distinct, so we've satisfied the original question.